6 flashes of light. That is what the Artemis II crew saw when they swung around the far side of the moon on April 6th, 2026. 6 rocks from deep space detonating on the lunar surface, bright enough to see with the naked eye from 4,000 miles away. No warning, no sound, just light and then nothing. Here is what nobody is telling you about that moment. We have been planning to send humans back to the moon for over a decade. We have spent hundreds of billions of dollars on rockets, spacesuits, life support systems, and radiation models. We have run thousands of simulations. We have built artificial intelligence systems to map every crater, every ridge, every shadow on the lunar surface. And then 4 astronauts actually went there, looked out a window, and saw things that did not match a single prediction. The colors were wrong, the terrain looked alien, and the rate of impacts was higher than the statistical models suggested it should be. This is not a story about what Artemis II discovered. This is a story about what Artemis II revealed that we did not know we were missing. Because there is a difference between a model of the moon and the moon itself. And that difference, it turns out, is enormous. If you think space exploration is about confirming what we already know, this video will change your mind. Subscribe so you do not miss what comes next. Now, let us begin. Everyone talks about the rockets. Everyone talks about the budget. Everyone talks about which country is going to plant a flag on the lunar South Pole first. And those conversations are real and they matter. But they are all distractions from the problem that sits underneath all of them, quiet, patient, and almost never discussed in mainstream coverage of the Artemis program. The biggest problem with moon exploration is not getting there. We solved that in 1969. The biggest problem is that we have been designing everything, the suits, the shelters, the mission timelines, the radiation protocols, based on a model of the moon that is fundamentally incomplete. Consider the surface itself. Lunar regolith, the layer of dust and fragmented rock that covers the entire moon, is unlike any material that exists on Earth. Every grain is sharp, not rounded like beach sand that has been tumbled by water and wind for millions of years, sharp like freshly broken glass because there is no water, no wind, no erosion to soften the edges. These particles carry extreme electrostatic charges. They cling to everything. Visors, joints, seals, lungs. Apollo astronauts described their suits becoming stiff after just a few hours on the surface because the dust had worked its way into every mechanical joint. And we are planning missions that will last 6.5 days on the surface, not hours, days. Then there is the radiation environment. The moon has no global magnetic field. It has almost no atmosphere. This means 2 completely different categories of radiation reach the surface without any meaningful filtration. Galactic cosmic rays, which are high-energy particles accelerated by supernovae thousands of light years away, arrive constantly, day and night, penetrating metal, penetrating rock, penetrating the human body. And then there are solar particle events, sudden eruptions from the sun that can flood the lunar surface with lethal doses of radiation within hours of beginning. These 2 threats require completely different responses. One is chronic and cumulative. The other is acute and potentially fatal within a single afternoon. Here is the part that should concern you. Most of our radiation data for the lunar surface comes from orbital measurements and from the Apollo era, which gave us a combined total of roughly 300 hours of human presence on the moon across 6 missions. 300 hours spread across half a century. That is what our current models are built on. Artemis III will ask astronauts to spend 156 hours on the surface in a single mission. That is more than half of everything we have ever accumulated, compressed into one trip with one crew, in one location we have never visited before. The model is not wrong. It is just incomplete. And on the moon, incomplete can be the difference between a successful mission and a catastrophe that grounds human space exploration for another generation. Let us be precise about what Artemis II actually was. It was not a landing mission. The Orion spacecraft carried 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, on a free return trajectory around the moon. They flew within 4,000 miles of the lunar surface, swung around the far side, and came home. No boots touched the ground. The mission was designed to prove that the hardware works, that the crew survives, and that the deep space network can manage the communication challenges of lunar distance. What it was not designed to do was overturn assumptions. And yet, the 6 impact flashes are the detail that captured headlines, and they deserve serious attention beyond the spectacle. The European Space Agency's Neliota program, using a 1.2 metre telescope in Greece, detected 192 validated lunar impact flashes between 2017 and 2023. Statistical modelling from that dataset suggests the entire lunar surface receives approximately 7.4 sporadic meteoroid impacts per hour under normal conditions. During meteor showers, when the Earth and Moon pass through the debris trails left by comets, that number rises to 12.6 impacts per hour. The Artemis II crew observed 6 confirmed impacts during a 7-hour flyby. That is a rate of roughly 0.86 impacts per hour, visible from their specific vantage point, covering a fraction of the total lunar surface. When you adjust for the limited field of view from the Orion cabin, that observed rate is not inconsistent with existing models. But here is what the data cannot yet tell us. 2 of those 6 impacts occurred during the 40-minute communications blackout, when the spacecraft was behind the moon and Jeremy Hansen was the only witness. Those 2 events were observed by human eyes in lunar space and recorded verbally, but they could not be cross-referenced with ground-based telescopes in real time. That gap in verification is itself a data point about the limits of our current monitoring infrastructure. Then there is the far side. Astronauts reported that the colours and terrain did not match their expectations or their training materials. This is not a trivial observation from untrained observers. These are people who spent years studying lunar geology, who memorized topographic maps, who trained in simulated lunar environments. When they say something looked different, that statement carries methodological weight. The most likely scientific explanation is not that the maps are wrong, but that the interaction between human color perception, the specific lighting conditions of a solar eclipse geometry, and the actual spectral reflectance properties of far-side regolith produced a visual experience that existing photographic data sets taken under different conditions by orbital cameras with different spectral sensitivities simply could not replicate. In other words, there are things about the moon that only human eyes in that specific place at that specific moment can perceive. And that is precisely the kind of information that no satellite, no rover, and no simulation can generate. Finally, there is the biological data. Multiple crew members reported seeing phosphonies, brief flashes of light perceived while their eyes were closed, caused by galactic cosmic rays passing directly through their retinas and optic nerves. This phenomenon was documented during Apollo missions. It is not new. What is new is that we now have the ability to correlate those subjective reports with precise radiation dosimetry data collected by instruments aboard Orion, giving researchers the most detailed picture yet of exactly what the deep space radiation environment does to the human visual system in real time. That data is still being analysed. The conclusions are not final, but the picture emerging from Artemis II is not one of confirmation. It is one of productive disruption. Every assumption it tested came back slightly different from the prediction, not wrong enough to invalidate the models, just different enough to demand that we update them before we send people to live on the surface. Here is where the story gets genuinely uncomfortable. Science is not a collection of facts. It is a collection of models, and models are only as good as the data that built them. For 53 years, our models of the lunar environment have been built on 3 sources: remote sensing from orbital spacecraft, samples returned by Apollo missions, and the 300 hours of human surface time I mentioned earlier. That is an extraordinarily thin foundation for the decisions we are now making. Take the question of water ice. The scientific consensus, supported by data from multiple orbital missions, including the Lunar Reconnaissance Orbiter and the LCROSS impact experiment, is that water ice exists in permanently shadowed craters near the lunar South Pole. This is not speculation. The spectroscopic evidence is strong. Artemis III is being designed specifically to land near that region and confirm the presence, distribution, and accessibility of that ice, because if it is there in extractable quantities, it changes everything about the economics of long-term lunar presence. You can split water into hydrogen and oxygen. Hydrogen is rocket fuel. Oxygen is breathable air. A lunar water source is the difference between a base that requires constant resupply from Earth and one that can begin to sustain itself. But here is the tension. The models that predict where the ice is, how deep it sits, how pure it is, and how accessible it will be to the drilling equipment Artemis III will carry, those models are built on orbital data The actual subsurface thermal environment, the way heat moves through regolith at different depths across different seasons, is more complex than our current models capture. Small errors in thermal modeling translate into potentially significant errors in ice depth predictions, and drilling equipment designed for one depth profile will struggle with a different one. This is not a hypothetical concern. It is the same category of problem that caused the Mars Insight lander's heat probe, designed to drill 5 meters into the Martian surface, to fail after penetrating less than half a meter because the Martian soil behaved differently than the model predicted. The moon is not Mars, but the underlying epistemological problem is identical. We build models, we trust models, we design hardware around models, and then reality introduces variables the model did not account for. What Artemis II has done, quietly and without fanfare, is provide the first set of direct human observations in 53 years that can be used to stress test those models. Some of the results are reassuring. Others are raising questions that the scientific community is not yet ready to answer publicly, because the answers have direct implications for mission timelines and crew safety protocols that are still being finalised. The science is not stuck, but it is honest enough to admit that it does not yet know what it does not know. And that admission, in the context of sending humans to live on another world, is the most important data point of all. Right now, as you are reading this, galactic cosmic rays are passing through your body, not occasionally, constantly. Every second, roughly one high energy particle born from a supernova explosion somewhere in the Milky Way passes through every square centimeter of your body. You do not feel it. You cannot detect it. But it is happening and has been happening every moment of your entire life. You are alive and unharmed because of two things. Earth's magnetic field deflects a significant portion of incoming charged particles before they reach the atmosphere. And the atmosphere itself, 6,000 kilometers of it, absorbs and scatters much of what gets through. Together, these two layers of protection reduce your radiation exposure to a level your body's repair mechanisms can manage without catastrophic consequence. On the moon, neither of those layers exists. A person standing on the lunar surface receives a radiation dose approximately 200 times higher than a person standing on Earth under normal conditions. During a solar particle event, that number can spike to levels that, without adequate shelter, become life-threatening within hours, not days. Hours. Now consider this. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen experienced that environment during a flyby. They were inside the Orion spacecraft with its radiation shielding moving through cislunar space for 10 days. Their total radiation exposure was carefully monitored and fell within acceptable mission parameters. Artemis III will place astronauts on the surface for 6.5 days outside in suits in a radiation environment. Our instruments have never fully characterized at ground level in the specific location where they will land during the specific window of the solar cycle when they will be there. The suits will protect them. The protocols will guide them. The models will inform every decision. But the models, as we have established, are incomplete. And on the lunar surface, the margin between incomplete and catastrophic is measured not in data points, but in human lives. To be fair to NASA and the broader scientific community, they are not walking into this blindly. The Artemis program has invested heavily in radiation risk mitigation. Orion carries the most sophisticated radiation monitoring system ever flown on a crewed spacecraft. The lunar South Pole landing site was selected partly because certain terrain features offer natural topographic shielding from some radiation vectors. The spacesuits being developed for Artemis III incorporate radiation dosimetry directly into the suit systems, giving astronauts and mission control real-time exposure data. There are shelter protocols. There are abort criteria. There are solar weather monitoring systems designed to give crews hours of warning before a significant solar particle event reaches dangerous levels. These are not afterthoughts. They represent decades of engineering work by thousands of people who understand the risks better than any single video can convey. And yet, in April of 1972, one of the largest solar particle events ever recorded erupted from the sun. It arrived in the vicinity of Earth and the Moon with a radiation intensity that, had astronauts been on the lunar surface at that moment, would have delivered a potentially lethal dose within hours. Apollo 16 had landed on the Moon 3 weeks earlier. The crew had already returned safely to Earth. The timing was, by any honest assessment, fortunate. We did not design for that. We got lucky. And this is precisely the pattern that the history of human spaceflight warns us about most urgently. The Space Shuttle program had conducted 24 successful missions before Challenger. Engineers had identified concerns about O-ring performance in cold temperatures. The data existed. The risk was documented. But 24 successful flights had built a confidence that quietly shifted the threshold of acceptable uncertainty. On January 28th, 1986, the temperature at Kennedy Space Center was below freezing. 7 people died. The universe does not grade on a curve. It does not reward confidence. It does not acknowledge the elegance of our engineering or the thoroughness of our simulations. It simply operates according to its own parameters, indifferent to whether our models have accounted for all of them. Artemis II gave us new data. That data is already being used to refine the models. That is exactly how the scientific method is supposed to work. The question worth sitting with is not whether NASA is being careful. The question is whether careful is the same as prepared. And historically, in the most honest moments of aerospace engineering, the answer has sometimes been no. So where does this leave us and what comes next? Artemis III is currently targeting a launch in the mid-2020s. It will attempt the first crewed lunar landing since December of 1972, placing astronauts near the South Pole in a region called the Shackleton Crater Rim, chosen specifically for its near-permanent sunlight for solar power generation and its proximity to permanently shadowed regions where water ice is expected to exist. The mission will carry a drill. It will carry spectrometers. It will carry instruments designed to characterize the radiation environment at ground level with a precision that orbital data simply cannot provide. That data will be the most valuable scientific return of the entire Artemis program. Not because it will answer the big questions, but because it will finally tell us which questions we have been asking incorrectly. The Lunar Reconnaissance Orbiter, now in its 16th year of continuous operation, continues to refine surface maps with increasing resolution. When Artemis III lands, mission controllers will be able to cross-reference real-time surface observations with the most detailed lunar atlas ever assembled. Discrepancies between what the crew observes and what the maps predict will not be failures. They will be discoveries. The Vera Rubin Observatory, which began its legacy survey of space and time in early 2026, will, over the coming decade, produce the most comprehensive catalogue of near-Earth objects ever compiled. This will dramatically improve our understanding of the population of meteoroids that cross the Earth-Moon system, which directly informs impact risk modelling for both surface infrastructure and crew safety during extravehicular activity. And then there is the Lunar Gateway, the planned orbital station that will serve as a staging point for surface missions. If constructed as designed, it will provide continuous monitoring of the cislunar radiation environment across multiple points in the lunar orbital cycle, giving researchers years of baseline data before any long-duration surface habitation is attempted. None of this resolves the fundamental tension at the heart of this story. We are making irreversible decisions, committing crews, committing hardware, committing national prestige based on models we know are incomplete. The new data will improve those models, but the crews going to the surface in the near term will be operating in an environment that is still, in meaningful ways, unknown. That is not an argument against going. It is an argument for going with open eyes, honest uncertainty, and the institutional humility to change course when the moon tells us something our models did not predict. The moon has been there for 4.5 billion years. It was there before the first single-celled organism appeared in Earth's oceans. It was there before the first fish crawled onto land. It was there before the first human looked up at the night sky and wondered what it was. It does not care about our timelines. It does not care about our budgets or our models or our confidence intervals. It simply sits in its orbit, absorbing impacts, grinding rock into dust, wearing the scars of 4.5 billion years of cosmic violence without complaint or explanation. What Artemis II gave us is not answers. It gave us a more accurate map of our own ignorance, and that in the long history of human exploration has always been the most valuable thing any expedition can return with. The crews who go next will be braver than the models that prepared them. The science that follows will be humbler than the assumptions that preceded it. And somewhere on the lunar surface, in a permanently shadowed crater we have never visited, in a radiation environment we have never fully measured, in terrain that looks different from 4,000 miles up than it does from the ground, there are answers waiting. We just have to be honest enough about what we do not know to find them.